Hi all. In this video, we are going to learn about a very important category of machine learning models, which are called probabilistic graphical models. So essentially, as the name suggests, these models are a marriage between probability theory and graph theory. So both probability theory and graph theory are used in many areas of science and engineering to model real life phenomena. And this particular class of machine learning models brings together the power of these two independent mathematical theories. And there are, of course, many kinds of graphical models which are possible, but largely speaking, there are two broad categories of probabilistic graphical models which are more popular and often used. One is what is called Bayesian networks, and the other are what are called Markov networks. So the primary difference between Bayesian networks and Markov networks is that Bayesian networks are directed acyclic graphs. By directed acyclic graphs means remind yourself of the decision trees we had learned in another previous video, where you had a root node, you had daughter nodes, and so on till you reach the leaf node. So that is an example of a directed acyclic graph where you have a particular direction of motion in the graph or in the tree. And this term acyclic means that it does not form a cycle in any part of the graph. So there is no subgraph in your graph which forms a cycle. That is what is Bayesian networks, and they are directed acyclic graphs, or what are also called DAGs. DAG. In comparison, the Markov networks are undirected graphs where there is no specified direction of motion along the graph, and you could move in any direction and they could be cyclic. So both of these have their own advantages and disadvantages. Primarily, DAGs are able to encode causal relationship. That is an important advantage that directed acyclic graphs have, and they are also easy to train. So if you have a given amount of data, DAGs can learn the underlying features a lot more easily as compared to undirected graphs. But there are some problems which have cyclic dependencies, and there of course you have to use Markov networks. So in general, both of them are powerful, have their own advantages and disadvantages, but in the machine learning community, Bayesian networks are more popularly used. So here, one important point to note is that these probabilistic graphical models are different from Markov chains. So what is a Markov chain? So for example, you might have seen graphs like this, where let's say you have some set of nodes. So let's say you have 3 nodes over here, and let it be that this node is happy node, this is the fine node, and let's say this is the sad node. So these are 3 emotional states that a person could be in. And now you want to model the transition between these states using some probability values. So let's say with probability 0.5, if you are happy to begin with, you will, let's say, remain happy. But with a probability of 0.3, you may change from being happy to being just fine. Or with a probability of 0.2, you may even transition from being happy to being sad. And similarly, you have similar transition probabilities for the other nodes. So let's say if you're fine, you will, let's say, remain fine for 0.3. From fine, you may convert to being happy with probability 0.4, and from here fine you may come to sad with a probability of 0.3. If you are sad, maybe you will remain sad with a probability of 0.8, and if you are sad with probability of 0.2, you may, let's say, transition to being fine. This is an example of a system with transition between different states of the system, and this is what is called a Markov chain. So the Markov property essentially means that your future state depends only on the present state, and it doesn't matter what state you were in the past. So for example, if you are fine, you will transition to these various states with various probabilities, but those probabilities do not depend in any way on what your previous state was. And that is why this is called a Markov chain. So it is important to understand that a probabilistic graphical model is very different from Markov chain. They may look similar, but the concept is very, very different. And it is different for the following reason, that in a Markov chain, the individual nodes are elements of a state space, and the edges denote the transition probabilities. Whereas in a probabilistic graphical model, the nodes are random variables and the edges denote conditional probabilities or causal relationships between different nodes. Let's understand this through a simple example. So now we are going to take a simple example of a Bayesian network and we are going to see how it works out. So let's say that one fine morning when you woke up, you found that the grass in your lawn outside your house was wet. So you found that the grass is wet, which is your final outcome. Now, why was it wet? There could be two reasons. Firstly, it may be that it rained. So that is a causal relationship that you have. And secondly, maybe your father or maybe your gardener opened the sprinklet in your garden, which sprinkled water all over the grass, because of which again the grass became wet. So both of these are possible. So there is a causal relationship between the nodes and the final output. Now whether it rained or whether your sprinklet was on also depends on whether the weather was cloudy. So there is again a causal relationship between the weather and your condition of rain or the sprinklet being on. For the simple reason, when the weather is cloudy, it is likely that it would rain and the probability of the sprinkler being on would go down, because if you think it is going to rain, you will most probably not switch on the sprinkler. So this is the primary difference between a Markov chain and a Bayesian network, because here edges denote the transition probabilities between these nodes, but here the edges do not represent the transition probabilities, they only represent the causal relationships between the two nodes. So cloudy and wet grass are not connected because there is no direct causal relationship between the weather being cloudy and the grass being wet. Only if it rains or if the sprinklet is on is your grass going to be wet. So Bayesian networks are represented using this kind of a directed acyclic graph. It is directed because, as you can see, there is a direction that you go from one node to the other, and it is acyclic because there is no closed cycle anywhere in this graph. Okay, so what do you do with this graph? There is nothing much that you can do currently. But if you provided the probability values for the various transitions, then there is a lot that one could calculate. So remember this simple figure, and now what we are going to do is to draw the probability tables for the various possibilities. So essentially we are going to represent each of the nodes with two possibilities. So if it is cloudy, answer could be true or false. If the sprinklet was on, again the answer could be true or false. If it rained, the answer could again be true or false. And whether the grass was wet, again the answer could be true or false. So now we need to write a probability table containing the various probabilities for all these different possibilities. So let's do that. So let's assume to begin with that whether your weather is cloudy is determined with a 50-50 probability. So with a probability of 0.5 your weather is cloudy, and with a probability of again same 0.5 your weather is clear, it is not cloudy. So now let's draw the transition for here. So here let's say your rain is equal to false, here rain is equal to true. For cloudy, let's say you have false and you have true. So now obviously if your cloudy is false, it is very likely that your rain is also false. And if cloudy is true, it is very likely that your rain is also true. So let us put 0.8 over here, 0.2 over here, 0.2 over here and 0.8 over here. Similarly, let's do it for the cloudy and the sprinklet part. So here you have sprinklet is equal to false and you have sprinklet is equal to 2. You have cloudy is equal to false and you have cloudy is equal to true. And now let's say if the weather is not cloudy, if it is clear, then let's say you switch on the sprinklet or you switch it off with a probability of 0.5. So let's say that the sprinklet being on or off when the weather is not cloudy is again 50-50. But if it is cloudy, then very likely you will not switch on the sprinklet because you would think that it is most likely going to rain. So if cloudy is true, then the sprinklet is going to be false with a very high probability. But in case your grass is very dry and it needs to be watered, then even when the weather is cloudy, sometimes you may switch on the sprinklet, because of which we are giving it a non-zero probability. So this gives us complete information as far as our Bayesian network is concerned about these two edges and this node as well. Now we need to have a table which models this relationship, the causal relationship between the rain and sprinklet and the wet grass. So let's draw that table next. So finally, whether your grass is wet or not, so let's say the wet is false is this option and the wet is true is this option, and this now depends on two possibilities. One is the sprinklet and one is the rain. So you have 2 into 2, 4 possibilities. Either both the sprinklet and the rain are false, either this is true and this is false, or this is false and this is true, and both are true in a very rare situation. Now let's fill up these values. So if the sprinklet was off and there was no rain, then clearly your grass is not wet. So wet grass is going to be false with probability 1. So let's put 1 over here and 0 over here. If your sprinklet is true and the rain is false, then your grass is going to be wet most likely, unless it is very hot and dry and all the water is evaporating very fast. So that's what it is. And the sprinklet is false, the rain is true, then again unless it is very hot and dry, your grass is again going to be wet with a very high probability. But if both the sprinklet and the rain is true, then with a much larger probability your grass is going to be wet. So let's make this 0.01 and let's make it 0.99. So now this graph and this table gives us complete information about the problem, and this is what a Bayesian network tries to do. So why do we use the Bayesian network? To make probabilistic inferences. So let's say using this information, we want to estimate the probability of the sprinkler being on given that the grass was found to be wet. So let's say in the previous page we saw this table where if you knew that your sprinklet and the rain are true, false, false, true, or whatever, you can predict that the grass is wet or not wet depending with these probabilities. But what about the other way around? That if you knew that the grass is wet, what can you say about the sprinklet being on or off? So this is the kind of probabilistic inference that can be done by using Bayesian network. So to do this, we again are going to use Bayes theorem. So first of all, this is equal to probability of S is equal to true and W is equal to true divided by probability of wet is equal to true. This is just simple probability theory, nothing else. And now this is equal to sum over the rain and the cloudy belonging to true slash false. Probability of S is equal to true, W is equal to true, R is equal to true comma false, and C is equal to true comma false divided by probability of W is equal to true. And now using the table we can calculate all these probabilities. I'm not going to go into all the details, but if you do the calculation, what you will find is that the numerator is 0.2781, the denominator is 0.6471, and the ratio is finally going to be 0.430. So this is finally the probability that the sprinkler was on provided your grass was true. Similarly, you could also calculate the probability of the rains being true provided the grass was wet, and if you do the same process, what you will find is that the probability is 0.708. So what does this mean? What this means is that if you found the grass to be wet, it is more likely to be due to rains than due to the sprinklet. So this is a kind of probabilistic inference, that you found that the grass was wet and now you are able to say that what was the reason why the grass was wet, and using these values that we have, we can infer that it is more likely that it rained than the possibility that the sprinklet was on. So now this is very very useful, but this also leads to a kind of a paradox which is called the Bergsons paradox. So what is Bergsons paradox? Let us try to estimate the probability that the sprinklet was on given that the grass was wet and it also rained. Suppose we have both this information, that the grass was wet and it rained, and now we want to predict whether the sprinklet was on or not. And if you again carry out the same procedure, the answer that you will get is 0.1945. So what did this do? So earlier, the probability of the sprinklet being on if the grass was wet was 0.43, and now if you have additional information that it actually rained, then the probability of the sprinklet being on actually goes down. And this is kind of a problem because in our Bayesian network model, the sprinklet and the rains are supposed to be independent. But because they have this kind of a causal influence structure, there seems to be an apparent relationship between the sprinklet and the rain. But strictly speaking, they are independent because they are being independently decided depending only on the weather. So this is a kind of Bergsons paradox that often comes in using when we use probabilistic inferences, and this is also sometimes termed as selection bias. That when there is actually no causal relationship between the two, but there comes out to be correlation. So that's why in science we often say that correlation does not mean causation. So here there is a correlation between the sprinkler being on and the rain being true, but this correlation does not imply a causal relationship between the two events. So this was a short introduction to Bayesian networks, and Bayesian networks are very, very powerful in machine learning, but they are not so commonly used because they are difficult to apply. But still, in certain applications, they can be a very powerful tool of making probabilistic inferences. Now, one problem in real life situations is that often all this data, all these transition values about a given problem are not available, and one has to infer that from available data. Now, if you have complete access to the given data in all detail, then again making this table becomes somewhat easier. But in many real life problems, again, we do not have access to the complete data. Some part of the data is hidden from us. In that case, estimating these probabilities in a straightforward manner becomes difficult, and there we take recourse to what is called the expectation maximization algorithm, which is a very powerful tool of estimating these values under the circumstances that some part of the data is hidden from you. So in the next video, we are going to learn about this very interesting and very powerful expectation maximization algorithm, which has found many applications in genetics, in physics, and many other areas of machine learning and AI. So till then, stay connected.